Welcome to my ACC 2020 online presentation. My name is Bálint Patartic and I work in the Institute for Computer Science and Control in Hungary. I've been working on this topic with Bálint Vanek and Peter Saylor from the University of Michigan. We also acknowledge funding from the EU project FLEXOP and FLIPASED. In this talk, I'm going to outline a method to construct an uncertainty sample that maximizes the gain of an uncertain system at multiple frequency points. First, let me motivate this approach to uncertain systems by presenting a hard disk drive control problem. Let's say we have the measured frequency response of a collection of 50 hard disk drives. As you can see, the drives behave like a double integrator on low frequency and have several resonance peaks at higher frequencies. We want to pay extra attention to this when analyzing the closed-loop performance. Therefore, we construct an uncertain model that captures the resonance peaks observed in the measurements. We design, say, a lead controller that provides tracking performance on low frequency and sufficient roll-off for robustness. Then we want to know, for example, how the closed loop with this controller suppresses output disturbance. Therefore, we excite the system with a step disturbance with additional sinusoids added on to see the effect of the resonance behavior. This is the output of the closed loop to that disturbance. First, we simulate the nominal system. Then we run Monte Carlo simulations of 50 random uncertainty samples. We add the traditional worst-case uncertainty, which maximizes the gain of the system, but only at a single frequency, the critical frequency. For this problem, we also want to use an uncertainty that maximizes the gain of the system at all the resonance frequencies. This produces behavior that we want to be aware of when evaluating the performance of the closed loop. In this talk, I'm going to outline how to construct such an uncertainty sample. Let me define some basic notions. This is the uncertain system interconnection of our consideration. The uncertain system P is represented as an interconnection of a linear time invariant LTI system M and a dynamic uncertainty block delta. The uncertainty has a block structure, which means that it is composed of the block diagonal elements delta 1, delta 2, and so on. These are all stable LTI systems with H-infinity norm bounded by 1. The worst-case gain of the uncertain system P is the largest H-infinity gain from the input D to the output E over the set of structured uncertainties. In practice, we compute the worst-case gain on a sufficiently dense frequency grid. This leads to skewed structured singular value calculations, or skewed mu calculations, as it is known in the control community. The computation of skewed mu is known to be NP-hard for most cases, therefore we approximate it by calculating upper and lower bounds. The upper bound u at a specific frequency omega is obtained by solving a semi-definite program that involves scaling the uncertainty channels. The lower bound L at frequency omega, on the other hand, is obtained by constructing a worst-case uncertainty that maximizes the gain of the uncertain system P at omega. Allow me to illustrate this further. This is the gain of an uncertain system as a function of frequency. The green curve you see is the gain of the nominal system. This blue curve is the worst-case gain lower bound frequency by frequency. That is, this is the maximal gain the uncertain system can attain at each frequency. The worst-case gain lower bound of the uncertain system is the maximum over all frequencies. Using the existing technique, we can construct a worst-case uncertainty that pushes the gain of the uncertain system to the maximum of the worst-case gain lower bound at the frequency where that maximum occurs. In time domain simulations, this uncertainty sample doesn't necessarily produce bad performance, since the gain of the system with this sample may be small at other frequencies. In our case, for example, the worst-case gain lower bound has a second significant peak at this frequency. However, the classical worst-case uncertainty makes the gain of the system less than the nominal here. Instead of this method, we propose an uncertainty construction algorithm with which you can obtain an uncertainty that maximizes the gain at several frequencies at the same time. In this example, the gain is maximal at both of the designated frequencies. This is the outline of how it is done. Worst-case matrix samples of the uncertainty are calculated at the given frequencies using the skewed mu power iteration. Then these complex matrices are interpolated block by block to form the worst-case uncertainty sample, applying the so-called boundary Nevel-Inner-Peak interpolation. In the rest of this talk, I'm going to provide details on these steps and a numerical example to illustrate the method. The backbone of our approach to uncertainty construction is the boundary Nevel-in-a-Peak interpolation. Here's how it works. This is the input of the algorithm. We have n distinct numbers on the imaginary axis of the form j omega and complex vectors u and v with magnitude less than 1. When we apply the interpolation, we obtain a rational matrix function delta of s with the following properties. Delta is stable, that is, analytic on the right half of the complex plane. It's norm-bounded by 1, that is, its largest singular value on the imaginary axis is at most 1. It also interpolates the data in the sense that delta times v equals u, and u conjugate times delta equals v conjugate at the given points. Note that if the data we want to interpolate is scalar, we set the v's to be 1, and then the resulting delta passes through the u's, as you would expect in any interpolation problem. Let us now see how the uncertainty is constructed. I'm going to demonstrate this using a sufficiently complicated numerical example. The uncertain system P is MIMO, multiple input, multiple output. It has 10 states, 3 inputs, and 4 outputs. The uncertainty consists of 3 MIMO blocks, each non-bounded by 1. This is the gain of the nominal system, and this is the worst case gain lower bound as a function of frequency. We pick 4 frequencies where we want to maximize the gain of the system. Note that the frequency omega-2 is at a global maximum and omega-3 is at a local maximum of the worst case gain lower bound. Omega-1 and omega-4 have no particular significance. These are added to provide a sufficiently rich example. These are the steps of the uncertainty construction. First, we have delta as an LTI system with 3 blocks. We apply the skewed mu power iteration at the given frequency omega k. We obtain a complex matrix sample of each block of the uncertainty. This sample drives the gain of the system to its maximum at the frequency omega k. Because of the properties of the skewed mu power iteration, the blocks of the matrix sample are rank 1. Since the blocks of delta are non-bounded by 1, the maximum singular value of the matrix blocks is less than 1. We use rank 1 decomposition to write the blocks as a product of 2 vectors, both with magnitude less than 1. At this point, we are ready to employ the boundary Nevel-in-a-Peak interpolation. For each block, we have a number on the imaginary axis, j omega k, and a pair of vectors with magnitude less than 1. However, if we use the interpolation right away, the resulting system will have complex coefficients. To get an uncertainty with real coefficients, we conjugate the vectors and assign the negative frequency minus omega k to the conjugated data. Finally, we apply the boundary Nevel-in-a-Peak interpolation block by block. Thus, we obtain a stable LTI uncertainty that has the correct block structure and maximizes the gain of the system at all the given frequencies. This is again the nominal gain and worst case gain lower bound of the system. When we substitute the interpolated uncertainty, this is what we get. Observe that the gain of the system with this sample indeed touches the worst case gain lower bound at the given frequencies. Let us compare this to the worst case uncertainty constructed using the classical method. With this uncertainty, the gain of the system is maximal at the peak frequency, but there is considerable drop at the rest of the frequencies. The difference between these uncertainties is clear in the frequency domain, but it isn't necessarily pronounced in time domain simulations. To illustrate that, let us look at the system in the time domain. This is the step response of the nominal system for one input-output pair. The dashed line indicates steady-state value. This is the response with the classical uncertainty, and this is the interpolated uncertainty. These two are fairly similar for this input-output pair. We could even argue that the classical uncertainty represents a larger deviation from the nominal. If we look at another input-output combination, however, the interpolated uncertainty produces remarkable behavior. The overshoot and the steady-state value are both considerably worse than with the classical uncertainty. There is a limitation of the gain maximization we have to discuss. This is again the gain of the system with interpolated uncertainty and the worst case gain lower bound. To illustrate the problem, we take a closer look at this section of the frequency response. On this frequency interval, we only picked one frequency where the gain is to be maximized, but there is a second peak at this frequency. Let's construct a new uncertainty that also maximizes the gain of the system here. This is the result we get. Notice that while the gain increased in the vicinity of this new frequency, it also decreased elsewhere. Let's pick yet another frequency in between these two and construct a third uncertainty. This is what we get when we do that. Again, the gain increased close to the new frequency, but decreased everywhere else. This means that we can't simply construct an uncertainty to maximize the gain of the system at a bunch of frequencies and expect the gain to be large at all frequencies. In other words, adding new frequencies doesn't necessarily increase the H2 norm of the system. Let me conclude the talk. I presented a method to construct an uncertainty sample that maximizes the gain of an uncertain system at several given frequencies simultaneously. The method consists of using the skewed mu power iteration to collect worst-case complex matrix samples of the uncertainty at the given frequencies and interpolating these samples using the boundary Neverlina-Peak interpolation block by block. This method can be used to complement Monte Carlo simulations of uncertain systems, especially if the system has multiple resonance peaks. If you're interested in this topic, or you have any questions, feel free to contact me. Also, you can go to GitHub and download the algorithm along with the examples in the paper and try it for yourself. Thanks for watching, and I hope to see you in future conferences.